Good morning, champs. In this video, we solve our first creeping flow problem. The goal is not just to compute a result, but to learn how to simplify the governing equations and use them to solve a thin film flow step by step. We consider a thin oil film between a moving lower plate and a stationary upper surface. The lower plate moves in the positive x direction with velocity u infinity. The gap height is h, and the length of the lubricated region is L. We choose x along the film and y across the gap, so y ranges from 0 to h. We begin with the incompressible governing equations. First, continuity. Nabla.u equals 0. Second, the Navier-Stokes equations. Density times the quantity partial u over partial t plus u dot nabla u equals minus gradient p plus mu times nabla squared u. We now simplify step by step. First, we assume steady flow, so all time derivatives vanish. Second, we assume creeping flow, meaning the Reynolds number is much smaller than 1. In this limit, viscous forces dominate inertia, so the convective term can be neglected. Next, we use the geometry. The film thickness h is much smaller than the length scale L. Velocity variations across the gap are therefore much larger than variations along the length. This means the second derivative with respect to y dominates the second derivative with respect to x. We also assume the flow is mainly in the x direction. So the velocity field is u equals capital U of x and y 0, 0. The governing equation becomes partial p over partial x equals mu times partial squared u over partial y squared. This equation states that the pressure gradient is balanced by viscous shear. We now solve for the velocity profile. Rearranging gives partial squared u over partial y squared equals 1 over mu times partial p over partial x. The pressure gradient depends only on x, so it is treated as constant during integration with respect to y. Integrating once gives partial u over partial y equals 1 over mu times partial p over partial x times y plus c1. Integrating again gives u equals 1 over 2 mu times partial p over partial x times y squared plus c1y plus c2. We apply the boundary conditions. At the lower plate, y equals 0, the velocity equals u infinity. This gives c2 equals u infinity. At the upper wall, y equals h, the velocity is 0. Substituting gives c1 equals minus u infinity over h minus 1 over 2 mu times partial p over partial x times h. Substituting the constants gives the velocity profile. U of x and y equals u infinity times the quantity 1 minus y over h plus 1 over 2 mu times partial p over partial x times y times the quantity y minus h. The first term is Couette flow caused by the moving wall. The second term is pressure-driven Poiseuille flow. To determine the pressure gradient, we use a global condition. Because the chamber is sealed and the flow is steady, the net volumetric flow rate through the gap must be 0. The flow rate equals the width b times the integral from 0 to h of u of y dy, and this must equal 0. Substituting the velocity profile and integrating gives U infinity h over 2 minus h cubed over 12 mu times dp over dx equals 0. Solving for the pressure gradient gives dp over dx equals 6 mu U infinity divided by h squared. Finally, we determine the pressure distribution. Integrating the pressure gradient gives P of x equals 6 mu U infinity divided by h squared times x plus a constant. At the entrance, x equals 0, the pressure equals the ambient pressure PA. Therefore, the constant is PA, and the pressure field becomes P of x equals PA plus 6 mu U infinity divided by h squared times x. The pressure therefore increases linearly along the film. This result shows the mechanism of hydrodynamic lubrication. The moving plate tries to drag fluid forward. Because the fluid cannot escape, pressure builds up and creates a backward pressure-driven flow that cancels the net flux.